Hi. So, I talked about activation energy a little bit last time, and this is the energy that's required to get to the transition state, where bonds are stretched, but other bonds haven't formed yet. So it's a really very distorted state, and it's got quite a high energy. So you can imagine that the higher this energy is, the fewer collisions, even if they have the right orientation, the fewer collisions will have that necessary energy. And then the slower the reaction will be. And so the smaller the value of K will be. And this is absolutely true, that reactions with large activation energies tend to be very slow because very few collisions are able to sort of come up with that energy. It's just a lot of energy. And reactions with small activation energies tend to be quite fast. Okay, I'm going to go back to OneNote now. Okay, so in order to talk about the role of activation energy in determining a rate constant, how much the activation energy matters in terms of whether the rate constant is going to be large or small. In order to talk about that, I've got to go back to that nasty equation that I gave you before, which is called the Arrhenius equation. So again, this is the Arrhenius equation. And just to review, this is the pre-exponential factor, which is equal to the collision frequency multiplied by an orientation factor, which is actually a fraction. This is really the fraction of collisions that have the proper orientation. And now we're going to be focusing on this part here, which we call the exponential factor. And I want you to notice two things that are in this factor. Okay, so I already pointed out the activation energy, but I also want to point out the temperature. And that's something we're going to be exploring here as well, is how does the temperature influence the rate constant? Okay, so first I want to just tell you, before we go any further, what this exponential factor actually turns out to mean, what it actually equals. And this is the fraction of collisions and with the correct orientation that have the required activation energy. So it's the fraction of collisions that have the required activation energy. Why is it that fraction? How does it come to mean that fraction? And what is this silly e to the minus something anyway? Okay, so I want to go over a little bit with you what this function is. So what is e to the minus ea over rt? What the heck is that? I have to go to a different thing because I kind of screwed this up, but I'm going to do that. Go to a new page. So we're talking about e to the minus ea over rt. Okay, so first I'd like to think about this in terms of being e to the minus x, okay, where x is this. So what I'd first like to do is consider, what is this? First of all, what is e? E is one of those mathematical numbers, sort of like pi, right? It's not at all pi, but it's one of those mathematical numbers that comes out of some pretty mysterious stuff that we don't, need to go into. But just like pi, pi, we know, everyone knows what pi is, right? 3.1415926, blah, blah, blah. E is actually approximately equal to 2.72, although it keeps going, okay? And so just like 10 to the x, so the log of 10 to the x is equal to x. The natural log of e to the x is equal to x. Is that right? Yeah. So those of you who know a lot of math, this is all very nice and everything. But for those of you who are not really into math, you can just think about e as being this number, okay? So when we say e to the x, okay, that's sort of like saying 3 to the x, because this number is about 3. So if we're thinking about functions, what does the function 3 to the x look like if you graphed it? So 3 to the x versus x. So let's think about that for a minute, okay? So what about 3 to the 0? Let's see, 3 to the 1, 3 to the 2, 3 to the 3. So here at 0, when x is 0, 3 to the 0 is 1. So there's that would be your first point. And then now we have x equals 1, and 3 to the 1 is 3. So that would be 3. And then you could see that 3 squared is 9, and 3 to the third is 27. So you see this function goes up, it goes up like crazy. It's and this is true of all exponential functions, that they rise extremely rapidly. Okay, so if that's what 3 to the x looks like, then what does 3 to the minus x look like? Okay, that's sort of our next question. So let's think about that, all right? So 3 to the minus x, so that function is going to decay very rapidly. So let's do the same sort of thing. Let's look at x being 0, 1, 2, or 3. So minus x is 0, minus 1, minus 2, minus 3. So 3, I almost wrote e, but I mean 3 to the minus x is 3 to the 0, which is 1. And then we have 3 to the minus 1. What is 3 to the minus 1? That's 1 over 3. All right, so that's 1/3. So it's, I'm just going to write it as 1/3. Then we have 3 to the minus 2. That's 1 over 3 squared, or 1/9. So what's happening to this thing? As we go further out in x, let me draw it a little better. What's 1 over 3 to the x, which is 3 to the minus x, which is a whole lot like e to the minus x. So 0 is 1, okay. Oh, I actually should have drawn it like this. Oh no, wait. Let me do that again. I'm getting a little bit wrong here. Right. So 1 is going to be the maximum value. So this is 3 to the minus x versus x. Okay, so here's 0. So when x is equal to 0, 3 to the minus x is equal to 1. When x is equal to 1, this is already down to 1/3. Here's 1/3 over here. So at 1, it's 1/3. It's over here. At 2, now it's 1/9. Okay. And here, 1 over 3 to the third is 1/27th. So by the time you get out here to x equals 3, this function has decayed like incredibly much. So 3 to the minus x is we call this a decaying function. It's exponentially decaying. So just the way 3 to the x is an exponential increase, a very fast increase with x, with increasing x, this guy here, we see a very fast decay. So this is an exponential decay, or decrease, as x increases. Okay, so e to the minus x, well, it really looks exactly the same. I mean, it's just a little bit different in terms of the numbers. But it starts at 1, and it goes down. So, didn't do a good job there, but there we go. This is e to the minus x versus x. Okay? So that's what the function looks like. Now, what we have, what we're interested in, is actually e to the minus ea over rt. Okay? So, and our x is EA over RT. So, and this is going to, of course, look the same. It's going to look like this. So what I need to do is focus on this EA over RT, okay? So why is this ratio in the exponent, you know, with this being the fraction of collisions that have the activation energy? So if we focus on this ratio, EA over RT ratio, okay? So